Welcome back. When we study systems or system theory, we are typically interested in a number of properties such systems might have. For example, we are interested if the systems are stable. An important property, since you might say that in general unstable systems are of not much use, whether they're causal, invertible, and so on. All these properties are independent of each other. One property does not require another property or does not lead to another property. Out of all possible 2D systems, we're primarily interested in systems that have two important properties. They're both linear and spatially invariant, thus forming LSI systems. We'll be introducing them in this segment. These two properties define an important subset of all possible 2D systems. Linearity means that if a sum of signals is at the input of a linear system, the system can process each signal separately and add up the processed signals. Spatial invariance means that it is irrelevant where the origin of the coordinate system is located. As we'll see in the next two segments, we can describe and implement LSI systems efficiently in the spatial domain through convolution. We can also describe them in the frequency domain, as we'll see in week 3. They're therefore friendly systems in that they reveal their properties to us in a rather straightforward way, but at the same time extremely useful and widely used in a number of applications. So let us see how LSI systems can be defined mathematically, and also let us look at some simple examples. So far we talked about signals, two-dimensional, multidimensional signals in general. We gave examples of some important signals such as the delta and the cosine that we will be using throughout this class. We are interested in processing or manipulating such signals through systems. So x, n1, and 2 is the input image to such a system. Y is the output, which is equal to a transformed version of the input, a manipulated version of the input. Some examples of such signals are y, n1, and 2 is equal to 255 minus x, n1 and 2. Assuming these images are 8 bits per pixel, therefore they range from 0 to 55, what such a system does is changing the polarity of the input, is turning black values into white and white values into black. So a negative into a positive or a positive into a negative. I can have another system that performs this transformation to the input values according to this function, and what such a system does is stretching the intensity values of the input image. We'll see actually quite a few systems of this nature when we talk about image enhancement. Similarly, you can have a system that provides an output which is equal to the average of the input values in a neighborhood denoted here by n. So this denotes a neighborhood of input values. And yet, as a final example, I can have a system that gives me as an output the median of the input values, again in a neighborhood. When we talk about systems, we are interested in a number of their properties, some of which are mentioned here. We are interested if the system is stable, whether it has memory or is memoryless, whether it's causal, whether it's linear, and whether it's spatially invariant. All these 5 here listed properties are independent of each other. A system can have all of them, none of them, just 1 or 2, and so on. And out of all these 5 properties, we are going to focus next on systems that have the last 2 properties. And to see such systems, we'll be referring to them as linear and spatially invariant systems, are quite useful, are used very widely, and it's relatively straightforward to describe such systems both in the spatial domain as well as in the frequency domain. A two-dimensional system is linear if it satisfies the homogeneity property shown here. In other words, if at the input of the system I put a weighted sum of two signals, the weight is alpha 1 and alpha 2, and if at the output I find the weighted sum of the individual outputs, so alpha 1, the response of the system to x1, plus alpha 2, the response of the system to x2, then the system is linear. This is clearly a very useful property because in many applications I have to process the weighted sum of individual images, and it might be easier to process each image individually and add up the responses. Or looking at it the reverse way, in some sense, I can take any signal and decompose it into simpler signals, simpler images, which then I process individually, and again I add up the individual responses. From this equation, it's clear that if alpha 2 is equal to 0, then the response of the system to alpha 1, x1, n1, and 2 is simply alpha 1, the response of the system to x1. So if an image is multiplied by a scalar, I don't need to be concerned. I can process the image and then multiply the output by the scalar. Similarly, if alpha 1 equals minus alpha 2 and x1 equals x2, since this property holds for any x1, x2, and any weight, then I see that the response to alpha 1 x1 minus alpha 1 x1, which is equal to 0, right? So it's the response to the 0 signal, is equal to alpha 1, the response to x1, minus alpha 1, the response to x1, which is equal to 0. So in other words, we see that if the system is linear, when I put a 0 at the input, I find a 0 at the output. Now this is a property that can be shared also by nonlinear systems. Therefore it's a property that I cannot use to prove that the system is linear, but I can use to prove that the system is nonlinear. And as a simple example, we can consider the system that we looked at in the previous slide. So using the notation here, yn1 and 2 is the response of the system to x as an input, right? And we define the system as 255 minus x n1 and 2, right? So such a system takes an 8-bit image and inverts it, finds the negative of it, right? So clearly, if I put a 0 at the input of the system, the output equals 255, which is different than 0, and therefore this system that finds the negative of an image is nonlinear. Generally speaking, it's rather straightforward to utilize this homogeneity property, this equation that you see here on top, and prove or disprove that the system is linear. And this property and everything that we covered here in this slide applies to two-dimensional systems and signals, as well as one-dimensional, three-dimensional, higher dimensional signals and systems in general. Let us consider again a two-dimensional system T. X n1 and 2 is the input, y n1 and 2 the output. For such a system, if when I shift the input by k1, k2, I find that the output is shifted by the same amounts, k1, k2, then the system is spatially invariant. Another way to express this is that to say that the system does not care about the location of the axis, does not care where the 0, 0 point is located. This property is important by itself, but even more important when combined with linearity, as we're going to see right away. Now, this property is independent of linearity, so if we consider the system we looked at earlier, which for an input x n1 and 2 generates as output 255 minus x n1 and 2. So this system finds the negative of an 8-bit image. We saw that this system is nonlinear. Now, if I shift the input to this system by x n1 minus k1, so I shift it by k1, k2, and I put this as input to the system, the output is equal to 255 minus x n1 minus k1 and 2 minus k2, which is clearly equal to the shifted output. Therefore, this system is specially invariant, SI. So the system that takes the negative of an image is nonlinear but is spatially invariant. As another example, if I look at the system that multiplies the input by a time varying gain. So this C is a gain that changes according to the location of the pixel, n1 and 2. It is rather straightforward for you to verify that such a system is linear but is not spatially invariant or it is spatially varying. That's another way to express it. Again, this particular property holds true. Everything we talked about here holds true for one-dimensional, three-dimensional, multidimensional, in general, systems and signals. Let us look now at systems that are both linear and spatially invariant LSI systems. Such systems are used widely, and we have developed very useful and convenient tools to describe and analyze them. Now, such systems can be completely described by a signal that we'll be referring to as the impulse response of the system. As the name implies, if I put a delta at the input of such system and measure the output, which I'll denote by H, n1 and 2, this is again the response of the system to an impulse, and we will refer to it as the impulse response of the LSI system. This is not just a mathematical construct, but in many cases I can utilize the system, such as a camera, and point the camera to a printout that has black background and a white spot in the middle, or I can point the telescope that is orbiting outside the atmosphere, such as the Hubble Space Telescope, to a distant star in the dark sky, measure the response, and that's the impulse response of the system. Knowing the impulse response now, again, I can completely describe the system, which means for any input x, n1 and 2, I can find the output of the system, and this is equal to the convolution of the input with the impulse response of the system. So this double star here denotes the two-dimensional discrete convolution. So linear systems, or filters as we often refer to, perform convolution, discrete convolution. The convolution of x with h, as we will show, is equal to this superposition sum. K1 minus infinity to infinity, K2 minus infinity to infinity, x, K1, K2, h, n1 minus K1, n2 minus K2. We'll show some examples of performing convolution in the following slides. It's easy to verify by substituting variables that the convolution has the commutative property. So in other words, convolution of x with h equals convolution of h with x.